Welcome back to the Explainer. Today, we're taking a metaphorical journey into the anatomy of a matrix. We're going to literally dissect it to understand its geometric power in data science. We're drawing directly from Mike X. Cohen's work here to see how we transition from basic operations to the heavy-hitting analytical tools that actually power modern algorithms. It's so tempting to look at a matrix and just see, a static spreadsheet, just a boring grid of numbers. But as Mike X. Cohen points out, there is way more to matrices than meets the eye. They aren't just passive containers for data. They are actual engines of geometric transformation. So here's our anatomical map for today. First, characterizing the matrix. Second, mapping matrix spaces. Third, measuring true information. And finally, unlocking transformations. All right, let's jump right into part one, characterizing the matrix and summarizing its volume. Imagine you've got this massive data set and you need to summarize its entire magnitude with just a single number. How do you do that? Well, the answer is the Frobenius norm. You're basically just squaring every element, summing them all up, and taking the square root. Think of it as measuring the overall size or weight of your data. This is absolutely crucial for machine learning applications like L2 regularization or ridge regression, where we have to use this norm to keep our model parameters from just blowing up. And in practice, the Frobenius norm is incredibly reliable. If you multiply a matrix by a scalar value, its norm scales perfectly linearly. This predictability is a huge deal. It gives us a super accurate way to compute the distance between two different matrices, which is an optimization trick used constantly in algorithms for things like image compression. Another really vital metric is the matrix trace. It's honestly incredibly simple to calculate. It's literally just the sum of the diagonal elements of a square matrix. The trace actually represents the physical volume of a matrice's eigenspace. And fascinatingly enough, that Frobenius norm we just talked about, you can actually calculate it as the square root of the trace of the matrix multiplied by its transpose. Kind of neat, right? Okay, moving right along to section 2, mapping matrix spaces. Let's look at their internal geography. First up, we have the column space. Think of the columns in your matrix like primary colors of paint. The column space is the infinite set of all the possible new colors you can create by mixing or taking linear-weighted combinations of those original columns. To picture this, if your matrix has just one single column, its column space is an infinitely long 1D line passing right through the origin. Every point on that line is really just a scaled version of your original single vector. But this escalates quickly as we add more data. If you have two independent columns sitting in a three-dimensional universe, their column space forms an infinite, flat 2D plane. It slices through the 3D space like an infinitely thin piece of paper. By mixing your two columns, you can reach any point on that flat plane, but you are physically trapped there. There's no way to reach the space above or below it. Now, let's draw a sharp line here to compare two entirely different spaces. The column space asks, what vectors can we create? Like, can we find weights x to reach a specific target vector b? But then we have the mysterious null space, which asks the exact opposite. What non-trivial weights y will collapse our matrix entirely to 0? Formally, the null space is the set of vectors that multiply a matrix to produce the zeros vector. It might seem like a mathematical black hole, but it's actually the keystone for finding eigenvectors later on. And just as a quick anatomical side note, if you transpose your matrix first, the vectors that collapse that to 0 make up what's known as the left null space. So let's test this out. For the matrix we're looking at, can you find the vector y that collapses it to 0? Honestly, I'm willing to wager a Vegas-sized bet you can't easily guess the exact unit vector Python would output. Why? Because there are an infinite number of vectors that satisfy this. You might intuitively guess 1 and 1, but Python outputs the normalized unit vector, something like 0.707, purely for numerical stability. Geometrically speaking, the null space sits exactly orthogonal, like at a perfect 90-degree angle, to the row space of the matrix. And what is the row space? Well, just like the column space mixes columns, the row space mixes your rows. They are perfectly perpendicular because the dot product of every row with the null space vector equals 0 by definition. All right, let's hit section 3, measuring true information, or the actual capacity of our matrix. This brings us to matrix rank. Look, having a spreadsheet with 1,000 columns absolutely does not guarantee you have 1,000 dimensions of actual information. If your columns are just scaled copies of each other, they are completely redundant. Rank is a unique integer that counts only the uniquely independent columns. It essentially tells you the true, non-redundant payload of your data. Rank is honestly wonderfully multifaceted. It's not just about independent columns or rows. It represents the literal geometric dimensionality of your column space. Whether it's the number of dimensions containing true information or the number of non-zero singular values, for a data scientist, rank is the ultimate truth teller about how much unique information a dataset actually holds. And you've got to remember this golden rule. The absolute maximum possible rank of any matrix is the smaller of its row count or its column count. If a matrix hits that maximum possible rank, it's considered full rank. If it's less than that, it's reduced rank or singular, which basically means you have overlapping, redundant data clogging up your system. Finally, let's dive into Section 4, Unlocking Transformations with Determinants and Polynomials. So the determinant is a single number associated only with square matrices. Now, computing it by hand can be a real pain, but its absolute most critical property in data science is alerting us if our matrix is singular. If the determinant is exactly 0, the matrix is reduced rank. It's literally missing dimensions of true information and has a non-empty null space. And this builds into something incredibly powerful. If we shift our matrix by an unknown variable, let's call it lambda, and then force the determinant of this newly shifted matrix to equal 0, we create what's called the characteristic polynomial. Using some middle school algebra, this lets us solve for lambda, which reveals the matrix's core transformative variables. Which brings us to the end of our anatomical journey. I'm going to leave you with this provocative thought. When that lambda-shifted matrix hits a determinant of 0, it unlocks the eigenvectors. These are the pure foundational axes of your data, the directions that remain totally unchanged during transformation. But as for how we use those axes for things like principal component analysis, well, that is a beautiful mystery for our next explainer. Thanks for learning with us today.